Hello students, Mr. Courtney here. This will be the first in a series of videos over energy, and in this video I'm going to be talking about the nature and transfer of energy. We're going to look at the definition of energy, talk about ways in which energy changes occur, and then we're going to also explain what happens to energy during a chemical or a physical process. So we need to define energy. Energy is the ability or the capacity to do work or produce heat. So these, you're thinking of a photosynthesis, some people being strong, batteries, you all think of energy. So all these processes have the ability to do work or produce heat, and that is what we call. When we think about the different types of energy, we have either kinetic or potential energy. The potential energy is due to the position or composition of a substance, whereas the kinetic energy is due to motion, or we say energy of motion. So as this girl stands at the top of this ledge with the ball in her hand, it has potential energy. As she releases it and it drops, the potential energy is being transformed into kinetic energy. It had potential energy due to its position, and now because it's moving, it will have kinetic energy, which is the energy due to motion. When you think of different things, are all these, when you think of food, all these substances, gas, coal, all these substances that we eat or we use to produce energy, they have stored energy, so they have potential energy. When we talk about chemical energy, some energy is required to form chemical bonds, and that energy is stored in the chemical bonds themselves. And that energy that is stored in the chemical bonds is called chemical energy, or sometimes it's called chemical potential energy. And it's called potential energy. It's a form of potential energy because the energy is stored. Any energy that is stored is potential energy. So in the food we eat, they're made up of chemicals or compounds. In the carbohydrates, we talk about carbohydrates. The chemical bonds that hold these compounds together, they contain the energy. So when these bonds are broken, energy is released. So that's how we get the energy from the food that we eat. And the law of conservation of energy, similar to the law of conservation of mass, we cannot create or destroy energy, but it's only converted from one form to another. So if you look, as the cyclist goes up the hill, he has kinetic energy. As he goes further up, the kinetic energy is converted into potential energy. So as he continues to go up, the kinetic energy is converted into potential energy until he gets to the top of that hill, where he has only potential energy for a point in time. And as he comes down the hill on the opposite side now, his potential energy is converted into kinetic energy until he gets to the point at the bottom where he has maximum kinetic energy, zero potential energy, and at the top here he will have maximum potential energy, zero kinetic energy. But at any point, if he were to add the potential energy plus the kinetic energy, there will be the same value as when he started climbing up the hill. Sorry, as the kinetic energy he had when he started climbing up the hill. All right, energy changes occur as either heat transfer or work, or a combination of both. So when we think of energy changes, they can either occur as a heat transfer or work, or a combination of both. When we think of thermodynamics, we think of the study of energy. And the law of conservation of law of conservation of energy is also termed the first law of thermodynamics, which states that the energy of the universe is constant, meaning that the heat lost or gained is going to be equal. Whatever you lose, one is going to gain. The energy lost will be the same as the energy gained. So you don't create or destroy the energy, you just change from one form to another. And if you add the total energies from the different forms together, it will remain the same. The value we get will always be the same. When we think of temperature, temperature is a measure of the average kinetic energy of the particles in a substance. Now, When we look at this, not all the substances are moving at the same speed or at the same rate. So some substances have a higher kinetic energy than other, some particles, sorry, would have a higher kinetic energy than the other particles in the substance. But the temperature, the overall temperature of the substance is its average kinetic energy of the components of the substance. Faster moving particles equals a higher temperature. The slower the moving particles, the lower the temperature of the substances will be. So if you think of an object that is hot, that means its particles or it's the substance that make it up will be moving very fast. They have a high kinetic energy. Whereas cold substances, they have a lower kinetic energy. These particles that make it up will be moving very slow or at a slower rate. When we think of heat, heat is the heat is given the symbol Q, is referred to the thermal energy transferred from one object to another. And the heat will always be transferred from the warmer object to the cooler object. So in this case, we have equal amounts of water at 90 degrees and 10 degrees. So we look at how much, what would that temperature change be? What would the final temperature of each one be? Heat will be transferred from the hotter object to the colder object. Since they're equal mass at the end, because their temperature difference is 80 degrees, we take half of that and they're going to meet somewhere in the middle. They're going to meet at 50 degrees because they have equal masses. So they're going to equilibrate to that temperature of 50 degrees Celsius. So when we think of endothermic versus exothermic reactions, in an endothermic reaction, energy is released to the surroundings. And in an endothermic reaction, energy is absorbed by the system. So what is the system? What is the surrounding? The system is the part of the universe in which your attention is focused on what you are looking at. So in a reaction, it will be the substances actually reacting. The surroundings is the region in the immediate vicinity of the system, everything else in the universe. And the universe is the system and the surroundings together. So in an exothermic reaction, the system loses energy to the surroundings. In an endothermic reaction, the system gains energy from the surroundings. So when we look at measuring energy, all forms of energy are measured in joules, but there are other different units that we can also use to measure energy. For example, a calorie, and that's with a small c, is the energy required to raise the temperature of 1 gram of pure water by 1 degree Celsius. Or we have the calorie, which is nutritional energy. And then we have the kilowatt hour, which is seen on electric bills. So you can ask your parents, or you can ask, if you look at electric bills, you will see that is measured in kilowatt hours. You look at the nutritional values on your food labels, you will see there in calories with a capital C. So here's the conversion factors. 1 calorie is 4.184 joules. 1 calorie or nutritional calories, 1,000 calories. And a kilowatt hour is 3.60 by 10 to the 6 joule. So let's look at a question. A candy bar contains 225 calories of nutritional energy. How many joules does it contain? So we look at what we're given and what we want to find. We want to go from nutritional value or nutritional energy to joules. So we start with calories, and we want to go to calories, small cal, as I like to say sometimes, and then you go to joules. So we start with our 225 calories. We convert that to small cal. Since we have 1,000 small cals per unit of nutritional energy, then we convert to joules. 4.184 joules per calorie. That will give us 9.41 by 10 to the 5th joules. The complete combustion of a small wooden match produces approximately 512 calories of heat. How many kilojoules are produced? So we look at what we're given. We're given calories in terms of heat content, and we want to go to kilojoules. So we start with calories, we convert to joules, and then we convert to kilojoules. So we start with 512 calories, and we know that there are 4.184 joules per calorie, and that in 1 kilojoule we have 1,000 joules. So we do our calculation, 512 times 4.184, then we divide by 1,000. That gives us 2.14 kilojoules. And all we're doing here is just basically dimensional analysis, converting from one unit to the unit, using our conversion factors that we already have. Let's look at one with an energy bill using kilowatts. If an energy bill indicates that the consumer used 955 kilowatts of energy in July, how many joules did the consumer use? So we look at what we're given and what we want to find. We want to go from kilowatt hour to joules. So we start with our given 955 kilowatt hours. And we convert that to joules because we know that there are 3.60 by 10 to the 6 joules in every kilowatt hour. Our kilowatt hours will cancel, leaves us with 3.438 by 10 to the negative 10 to the 9, or since we rounded off to three significant figures, that will be 3.44 by 10 to the 9 joules. Let's talk about internal energy. Internal energy is the sum of our kinetic and potential energies. Or as we say, the E, the change in energy, internal energy, or delta E, is equal to Q plus W. Q is equal to your heat content, and W is equal to the work done. So our system versus surroundings. In an exothermic reaction, Q is going to equal to a negative value because the system loses energy. Okay, system loses energy, so Q is going to be some negative value. It's giving off energy. Since it gives off energy, that means our internal energy will decrease, so its value will be a negative value. In an endothermic reaction, it absorbs energy, so Q will be positive, and our internal energy will have a positive value, so it will be greater than 0. So how do we measure the heat transferred? The amount of heat transferred in a physical or chemical process depends on the type of substance and also its heat capacity. So the heat capacity is the thermal energy required to change the temperature of a given amount of substance by 1 degree Celsius. So it doesn't matter what amount you have. So the heat capacity now depends on the amount of the substance you have. So if you have a larger amount of the substance, it would have a higher heat capacity, meaning that it would require a large amount of thermal energy to raise the temperature by 1 degree Celsius. Here's a way to think about it. You're going to warm food in the microwave. Now if you have a certain quantity, the smaller quantity you have versus a larger quantity, if you heat them for the same period of time, they absorb the same amount of thermal energy, but the larger quantity is going to be cooler than the smaller quantity, which is going to be hotter, because that larger quantity had a larger mass. So it will require more thermal energy to give you the same temperature change. So that's why if you heat more food, if you're heating more food, then you have to heat it for a longer period of time than you would heat a smaller amount of food. Now when we get the specific heat capacity, we're talking about thermal energy required to change the temperature of 1 gram of a substance by 1 degree Celsius. So here we're specifying, that's where the specific comes from. We're specifying the amount of the substance that we need to change the temperature of by 1 degree Celsius. So it doesn't matter if you have 10 grams, 20 grams, 30 grams, 100 grams. The thermal energy required to change 1 gram of the substance by 1 degree Celsius is still going to be the same. So that means specific heat capacity does not depend on the amount of the substance. So even if I have 50 grams and its temperature is changed by 2 degrees Celsius. If I have 100 grams, its temperature will be changed by 1 degree Celsius based on the thermal energy we apply to it, if we apply the same amount of thermal energy. Because it's gram, temperature per gram, degrees. So heat lost or gained is calculated based on the mass of the substance, its specific heat, and the change in temperature. So Q is equal to mc delta T. Q is the amount of heat in joules. The mass, M, of the substance is measured in grams. C sub P, or just C. Some books use S, but I prefer to use the C. That's the way I learned it, and I'm just going to stick with using the C. All right, it's the specific heat measured in joules per gram per degree Celsius. Delta T is your temperature change, which is always going to be your final minus your initial. Where are you going from to? So when we think of from, that means we're starting at that. That's your initial. To, it's your final. Or if you're told in the question that the temperature changes by a certain amount, that means that's your delta T. You don't have to calculate your delta T. Now, if your delta T is positive, that means heat was gained. So Q is going to be positive. If your delta T is negative, that means heat was lost. Q is negative. And we can also use that to determine if the reaction is endothermic or exothermic. Whenever heat is lost, so you have a negative T, negative delta T, or a negative Q, that's an exothermic reaction. Whenever delta T is positive, heat was gained, so that means Q is also positive. A calorimeter is used to measure the amount of energy released or absorbed in chemical reactions or even in some physical changes. All right, we have two types of calorimeter. The one on the left is a bomb calorimeter, which we can use to measure nutritional value or nutritional energy of food. And the one on the right is just a simple homemade calorimeter when we put two styrofoam cups inside each other. And we can use that to determine the temperature change in a chemical reaction. Now it's important that we have a stirrer so we can stir the solution to make sure that the substances mixes evenly. So when we measure the temperature, we're not just measuring the temperature at one point. We're measuring the temperature of the solution. The heat change will be evenly distributed throughout the whole system and its surroundings. Okay, let's look at this question. The piece of iron shown below underwent the temperature change shown to the right. The specific heat of iron is 0.450 joules per gram per degree Celsius. Calculate the change in thermal energy and indicate whether heat was gained or lost. So we have our initial temperature and we have our final temperature. From the scales, from the balance, we can see that our mass was 121 grams, sorry. Our delta T. Our final temperature is 120 and our initial temperature is 100. Our change in temperature is 20. So to calculate this heat change or the heat change in thermal energy, Q is equal to mc delta T. We know what M is, we know what C is, and we know what delta T is. We put those into our equation, we multiply, and we get 1089 joules. We round that off to two significant figures. We get 1100 joules or 1100 joules. That's the two significant figures. Now, since this value is positive, that means heat was gained. So heat was gained. In this case, we can say the reaction is endothermic. So, suppose that I heated 235 grams of water from 25 degrees Celsius to 100 degrees Celsius to make a cup of tea. How much thermal energy was used to heat the water? The specific heat capacity of water is 4.184 joules per gram per degree Celsius. So let's look at what we're given in the question. We're given mass. We're given our initial temperature, T1, of 25 degrees Celsius. We're given T2, and we want to find Q. We're also given the specific heat of water in the question. So first thing we do, whenever you have these problems, if possible, calculate your delta T. If you're missing one of your temperatures, just leave it as it is, leave it as an unknown, and substitute the value you know. This will help you a lot when you're solving these problems. So always calculate your delta T before putting it into your equation. So we have 75 degrees Celsius. So now we want to calculate Q, which is MC delta T, mass times the specific heat times our change in temperature, and that gives us 73,743 joules. We run that off to two significant figures. That gives us 74,000 joules. Okay. Well, students, that takes us to the end of the first video in the series on energy. I hope these videos have been very helpful to you. If you like, you can go ahead and hit the like button at the bottom. You can go ahead and leave comments. You can post your questions. I'll try to respond to them as best as I can and as soon as I see those questions. All right, so this is the end of this first video. Until the next time, I'm out. Blessings.